sun makes a big difference, okay? So in your area, does anybody know what your latitude is?
It's between 40 and 41, so we usually go with 40.
Yeah, well, you have a choice of 36 or 48. So to be safe, I would use the 48. Okay, I'd rather overestimate a little bit than underestimate. Now, across the top of the chart, okay, the ones, this area right here, this is the hours of the day. So this is your day hours, 24 hours on the clock. Okay, so for every hour of the day, they've estimated the different cooling load temperature differences for the roof types. Now, the number one roof type, the bottom one, is going to be my roof type that has the loosest construction and the darkest roof. Okay, so this would be like your black asphalt shingles with very little insulation, okay, because it's going to give me the highest temperature difference. My attic's going to get the hottest. And we're talking peak hours. Okay, my number 14 down here is the roof with the white shingles that's as close to that's decently insulated and everything like that. Okay, so these tables, if you're not doing for exact, okay, this is a mechanical engineering thing to sort of do. Okay, because you have to figure out, okay, where my building is, hours in the day, and stuff like that. I don't expect you guys to really use these tables. I want you to understand where they come from, but I don't expect you to, like, okay, for your spreadsheet, what number am I going to be using in here? We have some estimates that we use as a standard in the industry. Does anybody have any question on this table?
Well, this is all relating to a roof with an attic below it?
Yeah, but there's other tables for roofs with no attics.
Yeah, I was going to say, what if you had a situation where you have like a flat roof with no attic below it?
Believe it or not, you use it more as a wall, okay? Because because it's flat. There's no space inside of that. So your CLTD is basically zero.
But I see with my question with that is, I know just in general, the flat roof being a dark roof and being right in the living area, it is like the craziest amount of heat gain through it you could imagine. Yeah, that's where you look at that. If you look at those other table, the table 4, okay, your heat gains are high. So if you look at, let's find a roof here. Hope I'm going in the right direction. There we go. Ceilings under, it's basically roof on exposed beams or rafters. Okay, that's a light colored roof, dark colored roof. Okay, we look at our U values. These are relatively high. Okay, so we're more worried about heat transfer if you don't have an attic. The only reason we worry about the CLTD, let me go back over here and I'll make one of my nasty little drawings again. The only reason we worry about CLTD is because, remember I said in one of my lessons that we did earlier this week, we have this attic space up here. Okay, and it's not conditioned, it's not insulated, okay, so my outside temperature, okay, is going to be, let's say 95, but this space here is still going to transfer heat down here. So that's why we're worried about the CLTD, because it sort of magnifies the heat. It kind of relates.
Now you have a flat roof.
Coming up.
You have a flat roof. Do I have any space in there for it to magnify the heat?
No. Insulated, not really.
Not really. I don't really have that temperature difference besides
the temperature difference that I have, remember, at the top of my spreadsheet on the first page, on the J1 form, I have a temperature difference.
Oh, there's the U value. Ah.
Also, was actually the be putting in for winter and summer.
Son of a bitch.
What? Someone's not on mute.
Yeah, that's me. Sorry.
Okay. So what was the question? I'm sorry.
I see you have it up at the top of that sheet. It says on the table 1, part of it says 97.5%. Design DB is 12. It's kind of gibberish to me. No idea what that really is supposed to mean.
Okay.
And then for design.
Yeah, it's basically our design temperatures. Okay, and the way we got that was that automatically fills based on the drop downs.
Really? Okay. I was looking at tables and I found that. I just didn't understand what the information meant. Because
this automatically fills. It's basically what our outdoor design temperature is. It's our average.
Okay, so then what do we expect the winter delta T to be? Because there's other spots on charts for that.
Right here. It's the heating temperature difference. The 58 on my sheet that I'm showing you.
Oh, okay. I'm sorry. It's very hard for me to see because I'm on a.
Oh, I'm sorry. Let me see if I can magnify that up a little bit for you.
I've been trying to follow along on my phone, but I haven't been able to open Excel until just now, so it's been really hard to follow along to see what you've actually been doing.
Okay, just so you know, the recordings are out there. If you totally need, or email me, I'm happy to help, okay?
Okay.
So, again, the design city and state is right there. Just drop down, select the state, and then you can also, there's a drop down for the city that you'll be able to see, and York is in there.
Yeah, I saw that. Okay, cool.
Okay, and that will fill out there, and that will actually start helping populate all the rest of this.
Yeah, that was my big problem, kind of where to start and how to get it in properly.
Hey, Chris, you said you were going to make the chart for this thing we're working on available, the CLTD. How soon would you be able to send that over to us that are on the morning call? Because otherwise we end up having to work morning and evening because we have to wait for that to show up on the site till later today.
I will go and I will either email it to you right after this call, and hopefully you can distribute oral food into your course right after this call someplace, maybe on an announcement or something, okay?
Okay, if you do send it to me, I can get it to the others.
Okay, I'd appreciate that. So I'll get it right over to you. Now, the other thing that I wanted to, again, let me finish where I was going on this, because I told you we have some, let me delete my lines off. I told you we have some magic numbers that we use. Manual J has exact tables for every version of roof. Okay, Table 4 has been replaced with a Table 4A that includes the temperature differences. Unfortunately, I do not have permission to post that publicly. I'm trying to get it. As soon as I get it, I'll pass those on. But the ones we use, if you have a light-colored roof with insulation above the ceiling, okay, you'll use a temperature difference, a CLTD of 49, okay? So, again, light-colored roof, okay, above a ceiling. I want you to use a temperature difference of 49. If you have a dark-colored roof with insulation above the ceiling, use a temperature difference of 55. That's sort of an average of over the whole 24-hour period. If you have a stone shingle roof with insulation above the ceiling, use a CLTD of 58. If you have an unvented attic, use a CLTD of 60. What do I mean by unvented attic? Anybody?
You're talking about an older, are you talking about an older attic that doesn't have the eave or ridge vent?
Yeah, I'm talking about an older attic that's just totally sealed. It's something that you will find that those attics get extremely hot, and it's going to affect your second floor of a house really badly, or first floor if it's a single-story house. Unvented attics use a CLTD of 60. Those are going to be very, very high. Okay, if you want a specific CLTD for your roof, email me the description of your roof color, shingles, and insulation, and the quality of construction. I'll send you the specific CLTD for your roof. I have the tables here. I'm just not allowed to post them without permission because it is copyrighted material. So again, if you want a specific CLTD, email me. It takes me 2 seconds to look it up on a table. Okay, give me roof color, shingles, or type of roof, insulation, and quality of construction, and I'll send you a specific CLTD. No problem at all doing that. I might even send you the screen capture or a picture of the table for you. But I just can't post the full tables. Any questions on this? Okay, and again, I'll make this sheet available. It's a PDF file. I'm going to clean it up a little bit so it doesn't look all weird. But that's the CLTDs. Okay, and I think you need those to finish your roofs, or the ceiling areas. The other thing that we talked about a little bit yesterday was the floors. Okay, if you have a situation where you have a floor over an unheated area, okay, floor over an unheated area, you again have a temperature difference. It's called a partition design temperature difference, okay. Your PTDH column, again, that's this one right here, okay. I've sort of put my cursor over it right here, and I know those people on very small screens sometimes have an issue seeing this. But this one right here, if it's a partition floor, in other words, between two areas of a conditioned space, talk to me before you fill in these values. You can do your U values, but I'll have to give you these two values. I don't think anybody here has this situation going on where I really have to worry about it.
What do you mean? When you said partition space between two conditioned, wouldn't that be if you had a heated basement?
If I have a heated basement that I keep at a very different temperature.
Oh, okay. So if the basement can be kept at the temperature of the first floor, you just don't do the floor.
I don't do the floor.
Okay.
My floors, I think, are partition floors because I don't, in between my first and second floor, I don't have like a crawl space or any. It's my ceiling for my first floor is basically the subfloor for my second floor.
Okay, no, in this situation, that's just, you're not going to have a temperature difference, so you're fine there.
Okay.
In this case, what I'm talking about is, let's say you're in a house, you're on your first floor, you're doing your basement. Okay, your basement is somewhat heated. In other words, you're not heating your basement to the same level as your house.
What, really?
So there's a temperature difference.
I do have electric heat down in my basement too. So.
Okay. Yeah, as I said, most of you folks will not have this situation, so that's why I want you to talk to me before you fill these out.
So am I using that then, or what?
No, you're not. You're just doing U values.
Okay. All right.
And you're going to use your basement floor, okay? If you're doing your basement.
Yeah, I did. I did the concrete, whatever it was.
Okay. So does anybody have any other questions I need to answer for you on ceilings or floors? Oh, and by the way, I'm not expecting anyone to be an Excel expert other than David. So if you have questions on Excel or can't get around properly in the sheet, just email me the sheet. Okay, if you have an issue,
and I can fix it for you, or I can tell you what the issue is. Nobody on this call, I don't expect you to be Excel experts at all. That's not what we're trying to learn, but the Excel tool sure beats doing this all by hand. So that's the only reason we're using it, is this is a decent chart that just beats doing it by hand. Okay, at the end of today's session, right after my PowerPoint, I'm going to talk about sections 12 and 13. Okay, because that's where we start. Once you're through 12 and 13, we can start really getting into our heat loads, our room by room. We'll talk about then duct loss and gain tomorrow. But we start getting to the point where you really can see what your building is doing, and we can do some reasonability checks. So let's go ahead, and I want to talk about the infiltrate, or I want to start talking about where we left off yesterday, which we were starting to talk about the procedures, and some of this we've already talked about, because some of this we've already talked about. So hang on one sec here. Okay, this is where we left off yesterday. We left off starting to talk about the process. You guys are well into the process already. We've identified the heating zones within a building. That's your rooms, okay, basically each room. We're doing the exposed surfaces. That's the outside walls and the windows and the doors. You've already come up with the net areas for each surface. That was our part 2 of our assignments, okay. We found the effective U factors, okay, and we found the temperature differences because we have that information on our Excel worksheet. So all of this you've already done up to this point. Okay. We've talked about the Q value, okay, the BTUs. If you start looking at your tables, if you start looking at your spreadsheet, we've actually we found the BTUs for each one of those things. We found the BTUs for the windows. We found the BTUs for the walls. You're now working on BTUs for the ceiling and the floors. Okay, so again, we're starting to get to the point where you're getting total heat loss rate for those zones. When you look down at the bottom of the column, we're just missing a couple numbers where you have a couple formulas that are not allowing you to totally finish the heat loads for each area. By the end of today, you will be able to get the total heat loss for each of the rooms. Finally, we look at a building summary table that shows the total heat loss rate for the entire building. Once we have that, what can we do with our total heat loss? What's the next step we're going to do?
Sizing the system.
Yeah, basically we're going to move forward and we're going to size the system. Okay? And we're going to be able to start looking at equipment that's available. Okay, they have the Ornell, which is a government agency, has an R value calculator that I'll be posting the link for, okay, for whole building energy simulations. Okay, they've moved it from where it is currently at, okay, where we thought it was going to be at. So I've had to go find a new link for that. I'll post that into the course. Don't worry much about that, but I do want you to know it's there. It allows you to actually build the wall, and it allows you to select like the different insulations and stuff like that for R values. It's a neat thing, and it gives you some dollars lost and dollars gained. So we know temperature difference affects our heat loads. Everybody remember where I put when I showed we went way back when there was a chart that if the temperature difference between out and in is sort of mild, there's less of a heat load than if that temperature difference is very great. It was the one where the marbles rolled around. Someone had way too much time on their hands. Okay, so temperature difference makes a big difference with heat loads. We use an average. Okay, if I reduce the inside temperature on a cold winter day, okay, I have less of a temperature difference. Yes, I'm going to make occupants very uncomfortable, but I have less of a temperature difference. Okay, so reducing the temperature on a cold winter day makes a difference. Moving to a warmer climate, of course, reduces heat load. It's not what everyone wants to hear,
but it's there. Okay, area of the building envelope. Remember, our Q, okay, equals U A delta T. Okay, so Q is the U value times the area times the temperature difference. Everything in this formula makes a difference. Okay, if I change the temperature difference, I'm going to make a difference. If I change the area, I'm going to make a difference. Okay? And if I change the thermal resistance of the building materials, I'm going to make a difference. Okay, adding insulation to the walls and ceiling makes a difference. But be careful, because we've talked about adding too much insulation, because every layer of insulation you add, you cut the value in half. Okay, so if I have 2 inches of insulation, or R19, and I add another R19, it compresses it a little bit. It's not going to be the same value anymore. It's not going to double.
If you're able to install, let's say you did an R19 in a 2x12 rafter, okay, and you put it in properly, it's not compressed, and you left about an inch airspace and you put another set in without compressing it, it's still reducing it? Or is it only reducing it because on average you're compressing some of the original?
If you leave an inch airspace, okay, you'll be okay. It's the airspace that makes a difference. If you put it right on top of each other, you're going to reduce it.
Okay.
It's that airspace. Remember, air is an awesome insulator as long as it's there and not moving.
Okay.
Okay, so like if in an attic situation, if you have insulation baffles laying down, and if you put like wire across the top of it, and staple the wire to hold it a little bit off the other one, like an inch, you'll be fine. Okay. Better window frames, sealing cracks, particularly around doors, reduces infiltration. But there's a downside to that as well. Can you make a house too tight? Yeah, you can make a house too tight. Okay. Then you go to a heat loss summary. Okay. What we use the summary for, as I just said, we check to see if anything is way out of line. Okay, when I've been looking at your spreadsheets, one of the things I do is I capture some of your numbers, and I'm looking to see if anything is majorly out of line. If I have a BTU loss currently for one of your rooms based on where you're at, okay, if I see a BTU loss of 12,000 BTUs as a heating loss, okay, I'm going to take, I know there's a number out of line. Okay, so when I'm looking at this, I'm looking for reasonability. It's called a reality check. Never do a heat load without just taking a look at a summary page and saying, okay, reality check. Remember, all calculations that you do with a heat load is based on one set of conditions. Every time the outside temperature or wind speed changes, the rate of heat loss also changes, or heat gain. Because equipment performance can vary with these changing conditions, to accurately predict the energy usage of a building requires many more calculations. I'm not worried about predicting annual energy usage. Okay, that's a mechanical engineer on large commercial construction projects. But this is what I'm really worried about. Is we are doing our calculations on one fixed set of conditions. Okay, there's going to be many more temperature differences. That's why, like, when I give you attic cooling load temperature difference, okay, or some of the other numbers that I've given you, I'm giving you worst case scenarios. Okay, I'm giving you that it might be 1% of the time in the winter months, okay, my extremes, or 99% in the summer months, again, my extremes. Okay, I'm not giving you what the average is for the year round, because your customers are going to be very unhappy if on a 95-degree day, which is sort of a peak temperature day, they're not going to be able to cool their house to 75 degrees.
Okay, or even worse, on a winter day, they're not going to be able to keep their house warmer than a 65 degrees. Yes, we have 1 or 2 days a year that are outside of design conditions, but that is what it is. But so fixed set of conditions. Never use the average, okay? If you say to somebody, or in your own house, if you say, the outside temperature never gets above 85 degrees for most of the year, and then all of a sudden you have a summer that's 95 degrees, like I think we're probably going into this summer, okay, you're going to be very uncomfortable through the majority of the year. So be careful about this. Don't minimize your calculations just to save money on equipment costs or make a bid look better. It is not worth it. Okay, look at wind speeds. If you're on the top of a ridge or halfway up a mountain someplace, okay, your wind speeds are going to be higher, so you probably want to go a little bit more extreme on your temperatures and on your infiltration rates, which we're going to talk about today. Any questions on that? Okay. The best estimate of a building's thermal load can be totally destroyed by pure operator skills. This means if you don't ask questions and if you don't understand the process and if you just rush through these things once you get in the field, okay, you can really mess up a building load. Okay, small things like putting in a BTU versus a U value can really mess up a load. Okay, then, okay, the other thing that this is talking about, operator may be the homeowner or the building owner as well. Okay, they did a study, and this was done in, I want to say Massachusetts, if I remember right. They did a study one summer, and they took identical sized families in identical sized homes. They did this in a development, in a housing development. And the energy usage varied 30% due to different lifestyles alone. Okay, there's one thing I never guarantee a customer. Does anybody know what that might be? What I'll never guarantee a customer?
Financial savings?
Yeah, I'll never tell them what their electric bills will drop or raise. I'll never tell a customer, oh, this system will cost you so much less in either fuel or electricity. You can't make that guarantee. You're not in control of the thermostats. You're not in control of fuel costs. You're not in control of electric costs. Those are all things you cannot control. Okay? So I am very cautious about guaranteeing that to a customer. Now, what you can tell a customer, if you design the system properly, that in this corner of the house, okay, if it's 75 degrees there, okay, it can be within 1 or 2 degrees on the other corner of the house, okay, or in different rooms. Again, all based on system design. You can talk specifically about the system, but don't get into energy cost and fuel savings. It's just too much of a risk. Okay, I've seen some contractors do that, and they usually end up in court. Okay, so we have the area U-value air exchanges. Okay, again, this is what you're doing, so I'm going to skip over that. But we need to start a little bit talking about cooling loads. Okay, cooling load is basically any heat gained through the envelope. The building envelope is my outside walls. We have internal zone temperature differences. Okay, different temperatures within the structure. Now, basically, in a residence, we don't worry that much about this. We worry about this in a big commercial building. Okay, and the reason we worry about this in a big commercial building is if this wall here is south-facing, and this wall here is north-facing, and if I have a 500 square foot building, this is relatively large. My south-facing side of the building, okay, the rooms over on this side of the building are going to heat up much hotter than the walls on the north side of the building. Okay, now the York campus is a very great example of this, actually. Okay,
can anybody tell me what's on the south side or the southwest side of the York campus? Think about the York campus. Where is the front of that campus?
Is it the front lobby? Isn't that where the office and the front lobbies are?
Yeah, it's where they have all the instructor cubicles and stuff like that. This area gets beat with sun, okay? And there's always air conditioning running there when someone doesn't mess up the thermostat. Okay, so this area is always hot. I mean, really badly hot. Okay, the other side of the building has a tendency to get somewhat cold. Okay, but so we're talking internal zone temperature differences. Could I use one thermostat through this entire building and make everyone comfortable? Not really. Okay, so that's what we're talking about, internal zone temperature differences. Solar gain, again, comes down to where the windows are. Solar gain. Sun beats on a side of a building. Now, if I have a brick wall that's facing south, okay, brick wall, sort of thick, okay, facing south, the sun starts beating on that wall, usually, depending on where you're at, usually around 11 or 12 o'clock, okay, because that's the direct south exposure. Okay, it takes a while for the heat to make its way through this wall. So even though the sun is beating on that wall starting around 11 or 12 o'clock, the internal effects may not be felt until late in the afternoon, 1 or 2 o'clock, 3 o'clock in the afternoon, and that wall may still be radiating heat off into the space until about 4 or 5 o'clock at night. So that's what we're talking about, solar gain. Okay, depending on the building materials, now glass is almost immediate, but brick, anything with heavy thermal mass, it takes a while for that heat to make it through. In the winter time, this can really help us out. When the sun goes down, my building materials are still putting heat in the space. But in the summertime, this is a problem. Okay, again, because the sun goes down and I'm still putting heat into the space. So I still have to maintain heavy air conditioning for quite some time. Artificial lights is a big cooling load. Okay, which gives off more heat? The incandescent lights of the past, the fluorescent lights, or LED?
Incandescent, by far.
Yeah, the incandescent light bulbs give off the most heat. What about fluorescent lights? Is it the bulb that gives off the heat, or is it the ballast?
No, it's the ballast.
Okay, ballasts give off the most heat. And then LED lights, by far, they're the more efficient, not only with power usage, but with heat generation. So, again, there's some benefits here, and the power companies are starting to give a lot of rebates on this. But take it into account, okay, if I suddenly have an office space, okay, that has always had a lot of fluorescent lights, okay, look around any commercial building ceiling if you have the drop ceiling, and if all of a sudden they start replacing all of those lights with LED lights, which is actually a project that's going on in a lot of areas, what's that going to do to my cooling needs? It's going to drop it. Okay, so all of a sudden I may have a system that's seriously oversized.
But your heating needs are going to go up.
My heating needs will go up, but most often in a commercial building, my cooling needs are going to be the biggest because people give off heat, right? So, I mean, so most often in a commercial environment, my cooling needs are the biggest use. So if I have an oversized cooling system, what happens in that space? What am I going to see as a primary problem that occurs in that space? If I have an oversized... What?
Could you start getting condensation?
Well, let's hope it doesn't get that bad. What's it going to feel like if I walk into a space that has an oversized cooling system?
It's going to be cold.
It's going to feel clammy. It's going to almost feel like a refrigerator. You're walking into a walk-in refrigerator.
Make sense? Because it's not dehumidifying. This is actually becoming a big problem. Okay, a lot of energy savings going on changing out light bulbs, changing out appliances and stuff like that. But man, it can really mess up a building climate. So this is a big problem. I suspect when you guys get in the field, you're going to hit this problem. Okay,
if a cooling system, if an air conditioner is primarily a dehumidifier, and it's oversized, why would it not dehumidify? I would think it would dehumidify even more.
Okay, let me turn around and answer your question with another question. What controls an air conditioner?
The refrigeration cycle.
No. What controls an air conditioner?
Oh, the thermostat.
Yeah, thermostat. So does a thermostat measure humidity, or does a thermostat just measure temperature, sensible temperature?
Just sensible temperature.
Okay, so if a system is oversized, is it going to run long enough to dehumidify?
No, it'll be shut down because people will get too cold.
Yeah, that's the issue. Okay, you're right that a oversized air conditioner you would think would dehumidify better. The problem is, by the time it dehumidified, everyone in the space would be way too cold. Make sense?
Yeah.
Okay. Electrical equipment and appliances make a big difference. Again, I want you to think about the York campus. Think about the temperatures you feel when you walk into the break room where the machines are. Does it always feel a little warmer? Okay, that area in there has a lot of equipment in it, a lot of refrigeration equipment that's just putting heat off into the space. So we want to make sure that those areas we identify when we do our cooling loads. Again, in a residence like you're doing now, I don't worry that much about it because you guys don't have big copiers and stuff like that. Okay, but when you start talking about office buildings, you want to be very aware of where they're going to be putting some of these heavy appliances. Copy machines are notoriously bad. Break rooms with large amounts of vending machines that have refrigeration in them. Commercial buildings such as restaurants. You have a lot of cooking equipment in there. Puts off a ton of heat. Okay, cooling a restaurant kitchen is a very big issue because we're also bringing in a lot of outside air. So all of this makes a big difference with heat loads. Okay, computers, refrigerators, freezers, ovens and stoves, infrared heaters in bathrooms, standalone appliances, whatever, make a big difference, okay? Humidity makes a big difference, okay? High humidity is uncomfortable. Anything over 50% humidity can grow mold. Sources of internal humidity can be cooking, standalone appliances, shower rooms, especially like in health clubs and fitness centers. Big issue there. Greenhouses in commercial buildings. Washers, dishwashers, clothes drying, people, animals, aquariums are all sources of humidity. Okay, you need to be very careful. And you need to realize that those exist, especially if you're looking at a building. If I walk into somebody's house, and if I see they have like 14 or 15 aquariums in there, all of a sudden and they're complaining that they're uncomfortable. Well, you know what? I'm going to tell you right now the problem is high humidity. The higher the humidity, the less you feel comfortable when you're trying to air condition. The more dehumidification that has to happen. There's solutions for this. I was in a house, I want to say about 3 years ago, taking a look at a problem that a company called me in to look at for my side gig. And they couldn't figure out what was going on. The customer was just constantly uncomfortable. Okay, looked around the house, and I saw a doorway off to the side of the basement. I was like, okay, what's in there? And, oh, you're the first guy that's asked about that. Yeah, can I take a look in that closet, please? Oh, it's not a closet. It's my hot tub room. Well, let's think about my jacuzzi room and the level of humidity that's going to be putting off into a building. Okay? You've got to find these things, and sometimes you have to look around. And again, this is more on a troubleshooting basis, but if I'm sizing a new system, I'm going to take a look at that. Humidity. I'm looking for things that put off humidity. How many people are in the space? What are they doing? Okay? If I have a bunch of people, if I have 100 people sitting around an office building versus 100 people in a nightclub, which is going to be putting off more humidity? It's a question. If I have 100 people...
Nightclub.
The nightclub, because people are up and active, okay, and half drunk. Okay, so they're going to be putting off more humidity than they're going to be in an office building where you're sort of inactive sitting around. Okay. All of this stuff is stuff that we look at. And matter of fact, your spreadsheet, the residential load spreadsheet, is going to be taking a look at occupancy. Okay, we look at daily maximum temperatures. Okay, usually between 2 and 4 p.m. Okay, is where we hit our daily maximum temperatures. I'm not saying always, okay, but that seems to be the average. So I'm going to go for the daily maximum temperatures. We've talked about solar gain. We've talked about where we hit the solar gain. Okay, sun starts coming up in the west, it's going to start hitting my west wall, but that isn't going to be my peak solar gain. Okay, because it's just coming up. The sun's not high in the sky at the west. Okay.
Hey, I do apologize. At least over here, the sun comes up on the east.
Oops, sorry about that. Yeah. Don't apologize for me not being totally awake. Okay, so when the sun is coming up, we have very low solar gain. That's the point I'm sort of trying to get to, even though I mixed up east and west. Okay, sun comes up, we have very low solar gain because it's not high in the sky. Over the course of the morning, we're coming towards the south, okay? And then we hit our peak solar gain. Okay, if you think about it, if you have a house with solar panels, if you have a house with anything solar, it's more on the south facing. Okay, and then you come over to the west, sun's coming down. Now, there's a good period in here, the 2 to 4 in the day period, where I have very high sun, sort of on the southwest direction. Okay, so my west wall and my south walls are going to hit the peak temperatures. Okay, and Dave, I know it's no excuse for messing up the directions, but yeah, this house is sitting exactly the wrong direction from mine, and that's why it's really messed me up. Sorry.
It just had to. I couldn't not.
Yeah,
Sorry.
it's fine. I don't mind. Okay. So again, air conditioning, we try to maintain a suitable temperature in all parts of a building. We want to remove humidity, okay? We want ventilation, and we try to remove as much dust, soot, and debris from the air as we possibly can. That's our goal of air conditioning, okay? We want to maintain a suitable temperature and humidity, free the air from excessive humidity during certain seasons, an adequate supply of ventilation. Okay, and that's just not for this. Air conditioning can also be, I mean, when you're moving air around in the heating season, aren't you doing all of these same things anyways? So air conditioning is just maintaining a suitable temperature and clean air. Comfort level, we talked about this when we did our psychrometric charts. Remember, we gave you a comfort level. Every book has a slightly different comfort level. Okay, it's based on relative humidity and space and dry bulb temperatures, and it gives you what the effective temperature is. Okay, so if I have a 30% relative humidity, okay, and if I have a dry bulb temperature of 76 degrees, I'm still going to feel cool. Okay, if I take that 76 degrees that my dry bulb temperature is, that's the temperature I can measure, and if I raise the humidity to 80% humidity, okay, yeah, I'm going to feel differently. It's going to feel a little bit warmer to me. Most people like being in a temperature between 69 degrees and 73, 74 degrees. Okay, people, and as you get older, you like getting into the 74s and 75s. What part of our population, other than age, really likes temperatures up in the 74, 75 degree point most often?
Other than age?
Other than age. Who in an office building is going to start complaining in the winter or in the summer if the temperature... Yes.
Women.
Yup. Okay. If the temperatures go too far down below there, okay, the women in the office buildings have a tendency to complain more often on this.
They can buy a new sweater.
Yeah, you can't quite tell a customer that, but what you can do is install a fake thermostat that they could twist all they want and nothing happens. Been there, done that. So, again, just be aware, different people, different genders, different age groups have a different level of comfort. Okay, everybody cannot be a winner in an office building environment, so you just pick one along with the building owner. I normally try going for right in the center of the chart, okay, because that way I'm safe. Okay, we want to make sure we efficiently cool room air during seasons of high outdoor temperature. We want to control humidity. I want to effectively heat room and efficiently heat room during seasons of low outdoor temperature. And we want to do this with equipment that's not cost prohibitive in purchase or maintenance. Okay, this becomes very, very important. Okay, I can have the enterprise of all cooling and heating systems. I can have it do everything. I can have it not cost me much every month. I can have it connected to solar panels, collect solar heat. I can have it store heat overnight to use in the night. I can have big tanks in the ground to store cool water that I've cooled overnight and used during the day. So I can basically have a piece of equipment that doesn't cost the customer much to operate. But there's a big difference between a $5,000 install and a $25,000 install. There's one that's cost prohibitive. You also have situations where people want equipment installed that is just going to be such high maintenance. Okay, if you have a customer in a residential environment, they don't want to see you out there every month, okay, to maintain their equipment. Okay, and the last few words you want to hear from a customer is, I'll maintain this myself, because they're just not going to do it, okay? Yeah, don't worry about the maintenance side of it. I can change the filters and clean that screen on my own every month. Yeah, that doesn't happen. Okay, so you want to always keep in mind the cost prohibitive and how often it has to be maintained. In a commercial building, I'm less worried about the maintenance because they know they have to maintain equipment. They know they're going to have to see us 4 times a year, or depending on whatever it is. We set up maintenance schedules. So that's very important. Okay, job of a home air conditioner is very simple. Move heat from inside your home to the outside by pulling heat out of the inside air. Again, we want to move heat from a place where it matters to a place where I don't care where it goes. Okay, again, heat inside matters. Outside, you know what? I really don't care that I'm heating the outside air by making my inside comfortable. I should probably, but I really don't. The energy to run the air conditioner is used by the motor that runs the compressor. The entire system will normally give about 3 times the cooling energy that the compressor uses. Okay, and again, that's because of the refrigeration cycle. I'm not going to go into that too much here, but because of the refrigeration cycle, we actually create 3 times as much heat movement energy than the compressor uses. That's just an average. We've talked about this. 12,000 BTUs is 1 ton of capacity. Okay, 12,000 BTU per hour is 1 ton. BTU is British thermal unit, the amount of heat required to change the temperature of 1 pound of water, 1 degree Fahrenheit. If you see an old kitchen, one of those wooden kitchen matches that you can barely find anymore, okay, that, when you burn it completely, that's about 1 BTU. Window air conditioners are usually sized between 5,000 to 2,400 BT or 24,000 BTUs. So basically, from a little bit under half a ton up to 2 tons is a window air conditioner. Home air conditionings, okay, we go from 1.5 ton to 5 tons. Okay, now, you might come across houses that are over 60,000 BTUs. What do you have to do if there's no residential air conditioners that are sized up over 60,000 BTUs? What do you end up doing?
2 units.
Put multiple units in, or go to a commercial unit.
And I don't like going commercial units in a house because the warranties are different. Most commercial units don't warranty for over a year, even if installed in a residential. Residential warranties can be up to 5, 10, 15 years, so I really try to avoid commercial units. What else is important about a commercial unit that might not work well in residential?
Well, the size and everything else. But I know my buddy in Connecticut is an electrician, just worked on a house where they actually have a chiller on the roof because the house is something like 20,000 square feet. Johnson Controls maintains it, but it is a residence.
There are outliers. I had one in the Beacon Hill area of Boston. The guy who used to own Hoyt Cinemas did work on his house. He had a chiller in the basement. But let's talk on the average. What is going to be your, and this probably comes back again to the electrician comment, but what is the average issue with a commercial air conditioner in a residential environment?
Ugly.
Uses more electricity.
I heard 2 answers. What was the one that? Go ahead.
Voltage.
The amperage for the service at the house.
Aesthetics.
Voltage and amperage.
The aesthetics is the one I was also looking for. I heard the amperage. Okay, that's important because most of our houses only have 200 amp service for newer construction and might have 100 amp service for older construction. What's about phase of power?
You're going to need 3-phase power, which you probably won't have available.
So most commercial units, okay, and I'm not going to say all, okay, because again, there's exceptions to every rule. Most truly commercial pieces of equipment have a 3-phase compressor. Okay, and again, the residential units, they also do have units in commercial buildings that are only single phase, but most of the heavier, over 5-ton units are going to start having 3-phase. So you got to be careful about that. But now let's talk about ductwork. What's the size of ductwork going to be like that I have coming out of anything over 5 tons? It's going to be pretty high, isn't it? It's going to be pretty large ductwork to get that airflow movement. Might I not want to go that heavy on ductwork? Might I want to use smaller ductwork so I can get through the attics, the crawl spaces, and everything?
Sure.
Okay. Most often, and again, this is a most, again, there's outliers, especially in some of the wealthier areas of Fairfield and Stamford, Connecticut, and some of those other areas. But most often, when you start hitting the 5-ton pieces of equipment, a good contractor is going to look into splitting that into 2 units. Okay, so we get a little bit of zoning. Rather than having this big energy use running at one time, if I can put these in different parts of the house, maybe one on the south side, one on the north side, in terms of the air handlers and the space it cools. I might be able to get a little energy efficiency if I zone these by breaking this down to 2 units. Does that somewhat make sense?
If you do something like what we were talking about, one in the basement for the first floor, one in the attic for the second floor, it greatly reduces the ductwork as well.
Yeah, and duct loss is a big issue. So, and the size of the ductwork, the cost of the ductwork. So again, when you start getting to the 5-ton units, that's probably the max unit size you want to put in a residence. And I'm talking air movement, okay? I'm talking the condenser with the air handlers. Chillers is another issue altogether. I love chillers, but in most residential conditions, people don't want to pay that type of price. Okay, so again, home central air conditioners, 1.5 tons or 1.5 to 5 tons. Air conditioners are designed with many things in mind, okay? Sensible and latent load. Sensible, heat I can measure. Latent, heat I can't measure but has to do with the change of state of water, okay? Condensation, humidity. The amount and type of refrigerant. The amount of air that flows across the air conditioning coils. The overall efficiency of the system. Did you know it's against the law to install under 12 SEER? 12 SEER is a measurement of the seasonal energy efficiency rating. Okay, it's SEER, S-E-E-R. It's a seasonal energy efficiency rating. It looks at an average of how much energy that system will use over the course of a year. Okay, I can't install under 12 SEER anymore. Okay, in some states, I can't install under 13 SEER because of the requirements of efficiencies. Okay, airflow across the coil. Okay, we have 2 coils in an air conditioning system. I have the evaporator, which is inside, and I have the condenser, which is outside. My system gets less efficient the dirtier the coils get. Dirt is a great insulator. So maintenance has to happen. So when you're installing air conditioning, you have to look at where you're installing this stuff. Maintenance has to happen. Blockage. Okay. People who plant trees around the condensers to hide it from the street. Okay. Those trees, those bushes can get too close and can really affect how well a system is working, and it will affect how well they're cooling the buildings. Internal loads, lighting, motors, appliances, people. Okay? All part of the internal loads. Now, there's a lot of other things here that could affect, especially in a house, but we can't size the equipment for them. We just have to have enough of what I call the leeway or the sort of a borderline fudge factor, because you have to be able to account for things like computers, cooking, bathing, showers, hair dryers, stuff like that. You just cannot have those things. You don't know whether or not they're going to be. You don't know how often they're going to be used. Air conditioners cannot independently control heat and humidity. The thermostat, this is what we were talking about earlier, thermostat, controlling the function measures sensible heat. Humidity is extracted from the air as a side benefit of the cooling process, but I cannot control an air conditioner based on humidity. The short cycling or oversized air conditioners runs only long enough to satisfy the thermostat. It doesn't adequately address humidity issues. So sometimes you have to put a dehumidifier in if this is a situation happening. As a building's sensible cooling loads are reduced, the run time of the air conditioner to reach the thermostat becomes shorter. Short run times cannot handle that latent heat, and we've already really talked about this. Systems improperly installed, sized, or improperly charged will not cool and dehumidify the air. Okay, so again, we want to be very careful on sizing. Bigger is not always better. Ductwork, duct leakage can greatly reduce the energy efficiency. Ducts have to be sealed. Okay, you can save
10 to 40% of your air conditioning costs by sealing leaking ductwork. Okay, and that's important to run around an attic occasionally and look. If you have an attic that the ductwork has been in there forever and you've never gone up there while the air conditioning is running, run your air conditioning on a nice warm summer day and go up there and look for the cold spots. You might be surprised. Okay, you got to seal ductwork. And ductwork sealing does not last forever. Okay, in other words, whoever installed it 15 years ago may have sealed the ductwork perfectly, but as things settle, as things heat and cool, move, the sealant breaks down after a while. Okay, and it does fall apart. Important to take a look at. So for air conditioning, again, we're calculating sensible heat loads for each room. We're looking at wall, ceiling, floor, loss for heating, and a gain for cooling. You're doing this on your spreadsheet already. We calculate the loads for the windows and doors. We add a solar load for the cooling. Okay, remember I had you guys do the different facing glass directions on your window, on your glass schedules. Okay, we looked at the different numbers for the different facing directions. That's the solar loads. Okay, we look at windows, glass doors, skylights for the solar loads. We look at air losses and gains for air exchange, infiltration, ventilation. That's the next item on the sheet we're going to look at real quickly. Okay, and then we're going to start in looking at equipment sizing. Okay, we're going to look at equipment schedules. The heat load calculation influence the system initial cost. That's the first cost. It looks at the ongoing cost, which is efficiency, and it looks at customer satisfaction. I keep telling you this. Customers do not want to think about the air conditioning or heating. They just want to be warm or cold. Okay, so you don't want to think about it. I don't want a customer to be worried about that furnace that's installed in the basement or the air conditioner in the attic. It's there. We change the filters every couple months, and it's there. Okay, I'm going to skip that. Okay, there's several pieces of software out there. I've talked about these before. Okay, I'm going to give you this sheet so you can, if you ever decide to do this in the future, I'll give you the links to the different software. I really, and this is not really an endorsement because I don't like endorsing products, but this is the one I've always used, is RightSoft. HVACR Calc is actually pretty decent. I just consider them, it's harder to work with than the RightSoft. RightSoft was the one that I showed you where I was able to draw out the rooms, and it's the one you have access to on the simulator server. HVACR Calc, you have to do a lot of hand entries. There's no drawing. This just happens to be the HVACR Calc screens. You see it looks quite a bit different than the RightSoft. Okay, so again, there's a lot of software and stuff out there that will do this for you. Don't spend money on a lot of software until you're in the field doing this, because your contractor will take care of this most often for you. Okay, so this is the RightSoft that I showed you. You draw out room by room, you put in the doors and everything. Again, if you want to play around with it, it is out on the simulator server. A couple days ago, I think last week, I went through that a little bit. Maybe if we have time, we'll look at that again. It actually does all your worksheets for you. Okay, this looks very familiar compared to the Excel spreadsheet that you're looking at now. It puts it all together for you based on your drawings and your window data and stuff like that. It allows you to select the different constructions, and I did demonstrate this all to you, where you can actually click on the window and you can look at the properties, and it allows you to select all the different types of construction. And it lets you put in shadings and stuff like that. So all of this stuff is now you can draw it out with software, but the Excel spreadsheet gives you all of this and actually does it pretty nicely. Okay, before I go back to the spreadsheet for infiltration, anybody have any questions on what I've gone over?
No.
Okay. Give me another 10 minutes here and let me just talk a little bit about the ventilation, and I want to talk about the infiltration line here. Okay, those of you on a small screen, again, I'm looking at line 12 or section 12 on my on the J1 form on the spreadsheet. Okay, we're looking at infiltration. Remember, infiltration is my average, the uncontrolled movement of air. Okay, basically leakage. Anything that is a yellow square, you can, there's a drop down. So if it's yellow, there's a drop down list. Okay, envelope leakage, you select, you have to guesstimate how tight is the house. Okay, when you walk through it, do you feel drafts? Are the customers talking about drafts? You have a choice between tight, semi-tight, average, semi-loose, loose construction. Okay, if you don't know, if you can't figure it out, go with average. If you know the customer has done a lot of, or you have done a lot of sealing of cracks and crevices, you can start going to semi-tight or tight. Number of fireplaces, again, just count the number of fireplaces. Okay, 1, 2, or 3 plus if you live in a sort of a mansion with 3 plus fireplaces. Wood stoves, people have asked me about. Does a wood stove count as a fireplace?
Yes.
Yeah.
What is the difference between a wood stove and a traditional fireplace?
You got a door you can close.
The biggest difference is a door. However, you are still dependent on the homeowner when that wood stove is not running. You are still dependent on the homeowner or whoever is in charge of it to close the dampers, right? Unless it's automatic dampers. So whoever said that I would count wood stoves as a fireplace, yes. Some people will argue that, and the reason is, well, it's enclosed, but there's still air movement in there. Now, if a wood stove, some of the newer wood stoves, they actually have air intake from the outside along with the smoke going back out of the house. So they also have totally sealed units. If it's a totally sealed unit, like a pellet stove that has outside air intake, I might not count it. Okay, but if it uses room air, I'm going to count it. Okay, white spot over here. Okay, we're starting to look at what is our total square footage of the heated and cooled area. So this is, you take all the floor area of the house, floor area, and that's what you're putting in here. So if you know your house has 1,800 square feet of floor area, you put that right in there. Okay, number of bedrooms, count the number of bedrooms. And by the way, if you have a bedroom that's converted to an office, is that still a bedroom?
Yeah.
Yeah. Okay, number of occupants. Okay, this right there is going to solve a lot of your, you have a lot of formula errors still showing up on your sheets. Now, here's the interesting thing. Okay, number of occupants is done on a room basis. Okay, now you can really mess yourself up here. Okay, where you normally put number of occupants is based on bedrooms. Okay, so if you have a master bedroom, okay, and if you have a number of occupants of, okay, basically let's go over here. If you have a master bedroom, okay, actually I put that in the wrong spot. If you have a master bedroom and you have 1.5 occupants for that master bedroom, okay, so just be aware of the number of occupants, okay, and let me show you something here. Okay, you see what's happening here? Number of bedrooms. See what's happening to the occupant line? If I have 3 bedrooms, it automatically selects 4 occupants. Why does it do that?
Two for the master and then one for each other.
Of 2 people.
Yeah.
Yeah, basically that's what it's doing, okay? It's counting that you have a master bedroom, so just be aware of that. And again, this doesn't always apply, so if you're doing this in front of a customer, okay, just be very careful of this. So if they all of a sudden say you take their 4 bedrooms, okay, and they see this 5 occupants, because you have to leave a copy of this most often with a customer once they accept a quote. It's the law in a lot of places. Once they accept this number, once they accept their quote, and they're going to argue, well, I don't have 5 people in this house. You have to explain that based on the number of bedrooms, that's what we have to size the property for. Okay? So don't get messed up on the number of occupants, because this is, again, it's a calculated field based on the number of bedrooms. Okay. Net area on the rooms. What's it looking for here? Net area. What's it looking for?
Is livable space?
Yeah, livable space.
So this is cubic feet.
Yep. Volume.
So for the net area on the rooms, we're doing the height, length times the and the width, right?
Yeah, you're looking for volume.
All right. And this is for step 4 of the final. Basically.
I know this is. I worry just about step 4. I'm looking for the infiltration. I'm getting a little bit ahead here. Okay.
Okay.
Okay. And I'm going to give you some very specific directions. I'll write it out for step 5. Step 4 is not. Step 4 we're dealing with infiltration. Okay. But I know some people are working ahead. Now, room occupants must match the total occupants, okay? So if I have a bedroom here, okay, so let's say this is bedroom 1. Okay, I have bed 2. Oops, let me get to the... And I have master bed. Okay, room occupants must match my number of, my total occupants in the building. Okay, so I have number of bedrooms, I have calculated occupants. Okay, your room occupants must match that number.
So you have to have the 2 for the master and 1 for the individuals.
Yeah. Because what it's doing, remember, it's putting cooling loads in here. You see how when I added the 2 here, it's counting what my cooling loads per person is.
What about just we only doing one floor of the house?
Yeah, that was my question.
If you're only using 1 floor of the house and not doing the bedrooms, just do me a favor, get a number in here based on your, and put the occupants in here, or you're not going to be able to get your infiltrations properly. Okay? Does that answer your question?
I mean, yes, because I have in the first floor I have 2 bedrooms, so it's gonna be only like 3 people, in that 2 bedrooms. So
yeah, just adjust based on whatever you have. Like if you have 2 bedrooms here, you have 3 occupants. Okay, so make sure that in each of those bedrooms you match that total of 3 occupants.
So in my case, I've got an office downstairs off the kitchen. Should I just make believe I've got 1 bedroom downstairs?
I would. Because
Okay.
again, this sheet is assuming that it's assuming a full house, and you never have a house without bedrooms.
No, the problem is all the bedrooms are upstairs. So okay.
Yeah, so in this case, just use your office as 1 bedroom and put 2 occupants in it. Okay, in any place where you have have this value here, you see this value error on the bottom of the sheet, there's a little pop-up that shows up in yellow. For example, when I click onto that cell, it says room appliance load must equal total appliance loads. Okay, so again, it's looking for like in the kitchen. So if I have a total appliance load over here, which is a selection, okay, if I say I have 0 BTUs of appliances, that's going to be fine. But if I select I have appliance load of 12,000, for example, your office, you might have computer equipment in there, or kitchen, we might have appliances in. Okay, it's very rare a house does not have appliances someplace in that house. So I'm going to, like in my kitchen, okay, I'll come over here and make a room of kitchen. Okay, and I'll come back down here to my appliances, and I'll put 12,000 BTUs, or 1,200 BTUs in there. Yeah. Okay, and all of a sudden, now I match my appliance load, so I'm fine. Because if you look at my block load, now the numbers match, and you see that value went away. Now,
is there a chart or something that helps us narrow in on, the size of the microwave, the size of the stove? I'm in an Amish house, so the refrigerator's propane run. I have my regular electric stuff is actually in the other room in the office.
There is a chart that I gave you guys. I'm trying to find it. I think it was the T10.
We never got T10 in the night class. We got 1, 2, 3, and 4.
Okay. He'll probably post it tonight as soon as I. Let me get that for you. But appliance load is very difficult to estimate. Okay, 1 watt. Okay, 1 watt of energy. Okay, comes down to 3,400 BTUs. Okay, sorry, 3.4 BTUs is a watt. Now, if you want to, and I'll put this in writing and when we get to that part of the assignment, okay? So if you want to calculate it out, you can if you know the wattage of the appliances. Now, a microwave, let me ask you a question. A microwave, am I even going to include that in my appliance load?
Why not?
How long of each day do you run a microwave?
Oh, okay. Okay,
And,
but now your 1 watt equals 3.4 BTU. My oven and stove's propane. The refrigerator in the kitchen's propane. So I can't do the electric.
Now your propane appliances should have on the label, on the data plate, that's someplace on that appliance. It should show you the BTU's output.
Okay.
Take a look at that, and if you can't find it, can you snap a picture of the data plate and send it to me?
Yeah.
Okay, because that's something I'm not that familiar with, but I know somebody who is, and I'll pass that on. But okay, so again, for infiltration and thermal gains, that's what we're doing. Okay. Is you're basically saying we want number of bedrooms, occupants, you want your cubic feet. So if we know our floor area is 1,800 cubic feet, and we know we have 8-foot ceilings, how are you going to figure out your cubic feet? If I have 1,800 square feet and I have 8-foot ceilings, how am I going to figure out my cubic feet? $1,800 square foot floor area
times 8.
Times 8. Okay, it's actually a relatively easy measurement. Now, if you have cathedral ceilings, I think somebody in here has mentioned you have cathedral ceilings. Okay, you have 2 choices. You can come close, or you could use math and figure out the area of that extra triangle. When you guys get these numbers put in, the 12, 13, and the 14, okay, you now are starting to get your total block.
No.
Does someone have a question? Okay. When you start getting to this point, once you get your infiltration and your internal gains in, we are now starting to get to the point where I have a subtotal. This is now, up to this point, my heating and cooling loads. I don't have my whole house in here, but you can see where you start getting a heating BTU and a cooling BTU, okay, when you start working through these numbers. Okay,
I'm sorry to interrupt. I'm at this point, but except my cooling BTUs is still showing value from that subtotal all the way up to the top three, those three.
Okay, where is it?
Going along with it.
Okay, did you put anything in the room net areas next to any of these?
Yeah, I did all those already.
Okay, send me your sheet and let me take a look.
Oh, wait, hold on. The net areas, I thought those were the window net areas.
Yeah, you're going to have window net areas, okay, and then you're going to have wall net areas.
Yeah, never mind. Okay. I haven't done that yet.
Is that the issue?
Yeah, I haven't done the walls yet.
Okay, if you still have an error, do me a favor, send me your sheet.
Okay.
Okay, because I'd rather help fix the problem than let it linger out there and get you frustrated.
Can you go down to your walls section?
I did not do my walls yet. Sorry.
How come you're getting those populated numbers in there then?
Because I don't. Because I have. It's up. It's probably has to do with something up here. That's what I'm saying.
Because I have that done.
You have all of that done. Send me
just like you do.
Okay, send me your sheet.
Okay. In your email?
In my email, if that's preferable.
Okay.
Okay, because I'll open it up real quick and I'll take a look for you.
Okay. Send copy.
Anybody else have a question? Okay, folks, I think I've confused you all enough for today. If you have any questions, you guys know I do answer my emails. If email is preferable, I answer text messages as well. Somebody sent me a text message yesterday with a video attachment. I have a real tough time following those through, so if you want to send me an email or something, I'll gladly help you out, but video attachments don't do well. So work on this, continue working through. Part 4 is posted. The guys in the night program, I will send you those tables that I referred to, okay, and we'll get those in your direction. Just give me a little bit after this call. I have another meeting that I got to jump into.
Okay,
Any
Chris,
questions?
real quick.
Yeah.
Yeah, real quick. If I'm, excuse me, if I'm doing the bedroom with my office, is there anything in this program, because I'm going to end up putting it under the office, or do I have to have it under the name bedroom?
No.
For the occupants?
Just the total occupants, wherever you put them.
Okay, so I can put it under office.
Yeah, room name I could care less about. Okay, neither could the program. Just try to make, it will not let you go forward if the total occupants don't match.
Understand.
Okay, because of the ventilation requirements in each space. Anything else?
Hey, Chris.
Yeah.
When it comes to like the solar multipliers, if you're not using the Excel program, how do we go about obtaining those?
Which solar multipliers are we talking about?
I'm talking about